So before we start thinking about the reactivity of alkenes and even the shape of alkenes, we have to think about the structure of them and the bonding that exists in an alkene molecule. So let's take a look at the simplest alkene, where you have a carbon-carbon double bond, and each carbon has a hydrogen coming off of it. And this is called ethene. Sometimes you'll hear it called ethylene. That's a common name that's associated with ethene. And if you think about the hybridization of ethene, the both of the carbons are sp2 hybridized, right? Because they have essentially three electronic or electron domains around each carbon. So we know the hybridization is sp2 hybridized. So let's take a look at what we get from that hybridization. Recall, carbon in its atomic uh, form has two electrons in an s orbital, and then two electrons that are unpaired in two separate p orbitals. Obviously, the bonding doesn't make sense using this particular model, just like we saw when we examined methane and thought about hybridization of methane. So since it's sp2 hybridized, we know we're going to take an s orbital and two p orbitals and create now three new orbitals. Remember, when you mix three orbitals together, you have to get the same number of orbitals out of it. This is um, this is true for hybridized orbitals. It's true for molecular orbitals, so keep that in mind. So if we create three new orbitals, we're left with one pz orbital. Of course, direction really doesn't matter that much. And when we place the electrons in the orbitals, we get three electrons in the sp2 orbital. And the p orbital is a little bit higher, but that one electron goes into it. It doesn't get paired with an sp2 orbital. And the reason for this has to do with energetics. A p orbital isn't that high in energy relative to the newly created sp2 hybridized orbitals. Okay, so now we have the orbitals. What does the atomic orbital picture look like in its entirety of that carbon atom? So if we think about it, we have three sp2 orbitals. They are trigonal planar, right? We know that sp2 hybridization produces trigonal planarity. And so how do we kind of represent that? Well, one way that we can do it is we can draw an sp2 hybridized orbital that's in the plane and in a kind of a horizontal fashion. Now, if we do this and we kind of think about how the other two are aligned, they could be certainly also be in the plane, but we could rotate 90 degrees and we could put one of them uh, out of the plane, coming out at us, and one behind us. And so if we draw that's the kind of a wedge um, for this particular sp2 hybridized orbital. So it's coming out, it's in front of us, and then we can draw a dash that is an sp2 hybridized orbital going behind us. So remember when we talked in the previous chapter about hybridization, the shape of the orbitals for an sp2 hybridized orbital is going to be about the same as the shape of an sp3 hybridized orbital, right? You have a big lobe and then a very small lobe, so it's like a skewed p orbital. Um, and so that's where these kind of lobe representations show us basically. So now we have the three sp2 orbitals. One's in the plane, one is coming out at me, and one is going back. And the bond angle between all three of them is 120 degrees. But we have a p orbital that's left over. And that p orbital is going to be perpendicular to the three sp2 orbitals. So now we're getting an atomic representation of one of the carbons in ethene. Now, the question is, well, how is that carbon bonded to the two hydrogens and to the other carbon. So, um, so let's take a look at the bonding of C2H4. So I'm going to draw the structure of ethene again. And if I think about the bonding between a carbon and one of the hydrogens, it's going to be the same as the bonding of carbon and methane and a hydrogen, except that instead of having an overlap of a 1s to a orbital with an sp3 orbital, you have a 1s overlapping with an sp2 orbital. And that is still a sigma bond because it's a cylindrical in shape, right? The question then becomes, well, what is this bond, this double bond? I mean, we call it a double bond. We know there are four electrons in it, two pair of electrons in it, but what does it actually look like? So in order to explore that, we have to, again, think about our atomic representation of carbon and how the two carbons are going to come together to form molecular orbitals. So I'm going to draw my representation again of that carbon, right, with um, the three sp2 orbitals. One's in the plane, one's going behind me, one's coming out at me, and then the p orbital. And if I think about where the electrons are, there's one electron in each orbital. So what happens? Well, a hydrogen 1s orbital comes in and forms a new molecular orbital with the sp2 orbital. And so we get a pairing of electrons because the hydrogen contributes one electron. And then we have on the other side another hydrogen 1s orbital coming in and pairing up its electron to form now another sigma bond. So these are sigma bonds that are 1s sp2 sigma bonds. Very similar in terms of the shape of the molecular orbital of a 1s sp3 sigma bond that we saw with methane. All right. So now we have on the other side a carbon. And what does the shape of that carbon look like? How is it bonded to this carbon that we have represented that has now the two hydrogens? Well, again, we're going to show the same representation, atomic representation. I have an sp2 hybridized orbital that's in the plane, but notice I'm basically going to draw the mirror image of the carbon on the left here. So I have an sp2 hybridized orbital that's a wedge, and I have an sp2 hybridized orbital that is a dash. And then I have a p orbital, right? And again, if I think about the electrons, the electron distribution, I have the 4 electrons, one in each atomic orbital. So now that carbon also is going to form molecular orbitals with hydrogen, just like we saw on the other side, and then the other hydrogen. And so now we have essentially the mirror of what we have on the other carbon. So each carbon has two sigma bonds from the overlap of the 1s orbital of hydrogen with an sp2 orbital of the carbon. Now, there are still two orbitals that can overlap, and these two orbitals are what's going to overlap to form that double bond. See, two orbitals forming two bonds between the two carbons. Well, what orbitals are left? Well, I still have in each carbon an sp2 hybridized orbital. And notice I also have a p orbital in each carbon, right, that can also overlap. Now, the way that they overlap symmetrically is going to be a little bit different, and so I'm going to get two different bonds. Let's think about how that happens. So what's going to happen? Well, the two carbons are going to come together, right? And so now I can, think about drawing them, and now they're going, the sp2 orbitals are going to come in and they're going to overlap with one another. So now I'm getting a true representation where I get this overlap, and now this new overlap is essentially a new molecular orbital between an sp2 of one carbon and an sp2 of another carbon. This is a sigma bond because it's cylindrical in shape, just like the overlap of a 1s to an sp2 is cylindrical in shape. The overlap of two sp2 hybridized orbitals is cylindrical in shape. And we can think about what that looks like by drawing a molecular orbital diagram, right? Where you have two sp2 hybridized orbitals that are coming together. And of course, we know that if you're mixing two atomic orbitals, you get two molecular orbitals. So the first one is going to be the overlap of the in phase, right? An in phase overlap. So the addition of two sp2 orbitals. And so I can represent that by essentially drawing a big lobe in the middle where most of the electron density is going to reside, and then two smaller lobes at the end. That's the addition. That's sp2 plus sp2, and that is our sigma bond, right? Because it's still cylindrical. As if I rotate about the axis, nothing really changes about it. Now, I can also do an out of phase addition, or sometimes we call subtraction, sp2 minus sp2. And what I get from that is now essentially, if you think about flipping one of the sp2 hybridized orbitals around, you basically get a node that's created, right? So here is a node between the two, and that's called a sigma star bond. So that sigma star bond, if we have enough electrons present and that sigma star bond is populated, obviously we wouldn't have a bond actually forming. But we know that each carbon contributes one electron, and so those two electrons go both into the sigma orbital, right? My new sp2 sigma orbital. And so I've created a strong bond here, right? Bond order of 1 because there are no electrons in the sigma star. Now likewise, I have a p orbital from each carbon, and that p orbital, those p orbitals can mix together. Now when I think about how those p orbitals mix, in terms of geometry, so I have so one p orbital I'm drawing here, the other p orbital I'm drawing there, and when they come together, they can come together in phase, the addition. So I'm essentially bringing them together, and so now both phases are in the same phase, and I create a pi, what's called a pi bond. Now I can also have them out of phase, and that creates my antibonding orbital. And notice how I draw the lobes. The lobes almost look like they're repelling one another, right? Which they actually are. Because they are out of phase with one another, they are going to repel one another, and I get this nodal plane. So we now have a pi bond, and the pi bond is different than the sigma bond because if you try to rotate about the x-axis in that pi bond, you actually would break that bond. And so we say that it has planar symmetry. Planar symmetry. And then, of course, we have our pi star antibonding orbital. And so now, when we when we take a look at that particular bond, we basically see that there's overlap between the two electrons in our p orbital here, right? And we create now a pi bond. And we can kind of demonstrate that simply by showing the lines, a dash between the two p orbitals. And sometimes you'll just see lobes of the p orbitals. So electron density that basically flows in between the two particular carbons. And I'll demonstrate that later on in the chapter, right? Okay, so one thing that's important to understand is because of the pi orbital, alkenes have no free rotation. So unlike alkanes, where you have free rotation, we can look at conformational analysis, alkenes don't have free rotation. And the reason for that has to do with that pi bond. So remember, we have this overlap of the two p orbitals, creating now a pi bond between the two carbons. And if you think about it, conformational analysis or rotation, if I rotate about that bond, so let's say I rotate about that bond 90 degrees, what happens? Well, now the hydrogens on basically the hydrogens on the right come into the plane, and the p orbital is perpendicular to the plane. So the two p orbitals on the two carbons can't overlap with one another, and therefore there's no pi bond. You break that pi bond. And the barrier of rotation is 66 kilocalories per mole, which is way too high for rotation at room temperature. Remember, rotation about a carbon-carbon single bond is about 4 kilocalories per mole, so a lot smaller barrier of rotation. And alkanes, basically, they have the freedom of rotation at room temperature. Alkenes do not. Now, the other thing that this tells us is that the pi bond is substantially weaker than a sigma bond. And this is going to be important. So if you look back on the table, previous table in Chapter 2, we saw sigma bonds have a bond dissociation energy of about 90. So we're going from 90 to 66 kilocalories per mole. And that means that pi bonds are more reactive than sigma bonds. And we're going to see how that plays out later on in the chapter.